Okay, so we hear a ton about AI writing poems or maybe drafting an email. But what happens when you take that same tech and forge it into a serious, industrial-grade tool for engineers? Well, in this explainer, we're going to cut through all the chatbot hype and really look at how AI is shaping up to be an incredible engineering co-pilot.
So that leads to the big question, right? How do you actually turn a general-purpose chatbot into a world-class engineer? I mean, how do you get it to the point where it can help design a jet engine, or discover brand new materials, or run these super complex physics simulations? That's really the core question we're going to unpack here.
All right, first things first, we've got to get one thing straight. A general large language model, an LLM, it's just the raw material. It's the starting point, not the finished product.
So think of a standard LLM like this. It's a brilliant student who's literally read the entire internet. They can talk your ear off about, well, almost anything. But, and this is a big but, they've never actually stepped foot in a lab. They've never opened a real technical manual. So to solve actual engineering problems, that raw intelligence needs to be armed with very specialized knowledge and a very specific set of tools.
Okay, so let's pop the hood and see what's going on inside. What are the core components that really make these models tick? And, more importantly, how do we adapt them for the super specific world of engineering? It all starts with how the AI learns to read. The process is called tokenization. And really, all it is taking a complex command, like a detailed design spec or a line of simulation code, and chopping it up into these tiny little pieces or tokens that it can actually process mathematically. This is the absolute first step. Without this, the AI has no idea what an engineer is even asking for. Okay, so now the AI can read. But just reading isn't enough, right? It needs to know what to focus on. And that's where something called the attention mechanism comes in. It's kind of like a spotlight. So if an engineer gives it a long, detailed prompt to design a part, this mechanism shines that spotlight right on the critical constraints. We're talking material type, stress tolerance, temperature limits, and it filters out all the extra noise.
You can't just toss a huge, complex engineering problem at an AI and hope for the best. It doesn't work that way. You gotta guide it. And that's exactly what chain of thought prompting is for. It's basically teaching the AI to think like an engineer. You break the problem down into smaller steps, you solve each one logically, and, this is key, you show your work. This completely transforms the output from just a black box answer into a reasoned, transparent solution you can actually follow.
All right, so we've got this core reasoning engine. But how do we take it from a smart student to a seasoned professional? Well, this is where we give the AI its engineering superpowers, and we do that by plugging it into specialized knowledge and real-world tools.
The very first upgrade is all about knowledge. A standard LLM, remember, learned from the internet, which means its knowledge is wide, but it can be kind of shaky, sometimes just plain wrong. So using a technique called Retrieval Augmented Generation, or RAG for short, we basically give the AI its own private expert library. Now, instead of guessing, it can look up the exact properties of a material from a datasheet or reference a specific building code. This makes sure its answers are grounded in hard, factual data. So the next big upgrade is literally giving the AI hands. I'm not kidding. Through something called function calling, the LLM can actually operate other software. So it can take a simple request in plain English and translate that into commands for a CAD program or kick off a complex fluid dynamics simulation. Suddenly, it's not just a chatbot anymore. It's a digital technician that can use the exact same tools a human engineer uses every day.
Okay, so let's see how this all comes together in the real world. What are the practical, game-changing things that are happening in workshops and labs right now because of this tech? And this is where it gets really, really cool. When you combine all these pieces, some incredible things start to happen. Engineers can just describe a design in plain English, and boom, a 3D model gets generated automatically. They can get help writing those insanely complex simulation scripts. Or they can even have the AI look at the results from an experiment, all those charts and tables, and explain what it all means. It's even being used to fast-track the discovery of new materials by predicting their properties before a single one is even made.
And this right here, this is a perfect example of the power we're talking about. Look at that sentence. It's packed with multiple complex engineering constraints. The AI has to parse this, understand the ultimate goal, pick out the specific material, the exact dimensions, and then use its tool calling hands to command the CAD software to generate a fully optimized design. I mean, this is automation on a completely different level.
But believe it or not, we can take this even one step further. When you combine that specialized knowledge, those real-world tools, and that step-by-step reasoning, you can start to build something way more powerful than just a copilot. You can build an autonomous AI agent.
So, what's an agent? Well, it's not just a tool that waits for a command and gives you one response. No, an agent is a system that can actually create its own plan, use a bunch of different tools to execute that plan over multiple steps, and it even remembers what it's done. All of this is in service of a larger goal, with way less hand-holding from a human.
So, how does an agent actually think its way through a problem? Well, a lot of them use a framework called REACT, which is just short for reason and act. It's a simple but powerful loop. So for example, first it might observe that a design has a weak spot. Then it will reason, I probably need to add a reinforcing bracket there. And finally, it will act by using the CAD tool to add that bracket. Then the whole loop starts over. It observes the new design, reasons about the next step, and acts again, just going step by step until the whole job is done.
But of course, this amazing technology isn't a magic bullet. It's not without some pretty serious challenges. As we push into this new frontier, we've got to be really clear-eyed about the hurdles we need to overcome and stay focused on the real goal here, which is collaboration.
And yeah, there are some major roadblocks. First up, hallucination. That's when the AI just makes stuff up. That is completely unacceptable when you're designing something like a bridge. Then there's safety. The stakes are incredibly high, and a mistake could be catastrophic. It's just non-negotiable. And finally, reliability. These tools have to work perfectly every single time. We have to solve these fundamental problems before these tools can be adopted everywhere.
And that really brings us to the most important takeaway of all this. The goal here is not to replace human engineers. Not at all. It's to create an incredibly powerful partnership. The whole idea is to build that copilot that can handle all the tedious calculations, the mind-numbing data analysis, the repetitive design tasks, and that frees up human engineers to focus on what we do best: creative problem-solving, critical thinking, and real, genuine innovation.
So all of this leaves us with a pretty fascinating question for the future. As these tools get woven deeper and deeper into how we work, will the next great, world-changing engineering breakthrough be designed by a human, an AI, or, and this seems like the most likely answer, a powerful, seamless collaboration between the two?